Subsea Pipeline Inspection, Engineering Comparison of Pulse Eddy Current, PEC, and Subsea Digital Radiography Testing, SDRT, Analyzing Advanced Techniques for Underwater Pipeline Inspections. Title: Purpose of Presentation, Agenda, and Inspection Decision Context, Subsea Pipeline Inspection Challenges, What is Pulse Eddy Current, PEC Operating Principle, Time Domain Response, PEC Capabilities for Subsea Pipelines, PEC Limitations and Engineering Implications, What is Subsea Digital Radiography Testing, SDRT. SDRT Operating Principle and Imaging Physics, SDRT Capabilities for Subsea Inspection, SDRT Limitations in Subsea Applications, Probability of Detection, POD, PC. Probability of Detection, POD, SDRT, Direct Comparison, PEC versus SDRT, Subsea Inspection Strategy, Best Practice, Engineering Recommendation, Why PC should not be replaced by SDRT, Risk, Cost, and Integrity Balance, Key Takeaways for Decision Makers, Conclusion and Final Statement. This slide introduces the engineering purpose of the presentation, which is to support an informed and defensible decision on the selection of non-destructive testing, NDT, methods for subsea pipeline inspection. Subsea pipelines operate in harsh environments characterized by hydrostatic pressure, marine growth, protective coatings, and limited accessibility, making inspection method selection a critical integrity decision rather than a purely technical preference. The focus of this presentation is on comparing Pulse Eddy Current, PEC, and Subsea Digital Radiography Testing, SDRT, two advanced inspection technologies that are frequently considered for external subsea corrosion assessment. The objective is not to declare a universal, best method, but to explain how each technology performs under real subsea constraints, what defect mechanisms they are most suitable for, and how they align with inspection objectives such as screening, sizing, and integrity validation. The presentation is structured to guide engineers, integrity managers, and inspectors through the inspection philosophy, technical principles, limitations, probability of detection, POD, and cost-risk trade-offs. Speaker emphasis should clarify that this comparison aligns with industry practices in offshore oil and gas, where inspection strategies are risk-based and typically employ multiple complementary NDT techniques rather than relying on a single method. The final outcome of the presentation is a practical engineering recommendation that can be justified during audits, regulatory reviews, and internal technical authority approvals. This slide outlines the logical flow of the presentation and establishes the inspection decision context. The agenda begins with a brief overview of subsea pipeline inspection challenges, followed by a detailed explanation of Pulse Eddy Current, PEC, technology, including its operating principle, advantages, and limitations. This is followed by an overview of Subsea Digital Radiography Testing, SDRT, focusing on digital detector-based radiography and its application underwater. A structured comparison section then evaluates PEC and SDRT across critical criteria such as detectability, resolution, deployment complexity, safety, cost, and probability of detection, POD. The agenda concludes with an engineering decision framework and a final recommendation. From a speaker perspective, it is important to emphasize that subsea inspection decisions are rarely binary. The inspection objective, whether screening, defect characterization, or acceptance, drives the method selection. This agenda reflects a risk-based inspection, RBI, mindset consistent with API and DNV philosophies, where screening tools are used to identify suspect areas and higher resolution techniques are deployed selectively. The audience should understand early that the comparison is structured to support lifecycle integrity management rather than one-off inspection activities. Subsea pipeline inspection presents unique engineering challenges that significantly influence NDT method selection. Pipelines are typically protected by multiple layers, including fusion-bonded epoxy, FBE, three-layer polyethylene or polypropylene coatings, and in many cases concrete weight coating for stability. Over time, marine growth accumulates on external surfaces, further increasing lift-off distance for inspection sensors. Access is limited to diver or remotely operated vehicle, ROV, deployment, which constrains inspection speed, probe stability, and equipment size. Environmental factors such as water depth, currents, visibility, and temperature also affect inspection reliability. Additionally, subsea pipelines often extend for many kilometers, making full coverage high-resolution inspection economically impractical. From an integrity perspective, the dominant degradation mechanisms include external corrosion, coating damage, microbiologically influenced corrosion, and mechanical damage from third-party interaction. The speaker should highlight that these challenges explain why traditional contact-based ultrasonic testing, UT, and manual radiography are rarely feasible as primary tools subsea. Instead, inspection methods must tolerate coating, marine growth, and remote deployment while still providing meaningful integrity data. This context sets the foundation for understanding why PEC and SDRT are evaluated differently compared to topside or onshore inspections. Pulse eddy current, PEC, is an advanced electromagnetic inspection technique used to assess wall thickness and detect corrosion in conductive, typically ferromagnetic, materials. Unlike conventional eddy current testing, which uses single or multiple sinusoidal frequencies, PEC operates in the time domain by applying a short-duration electromagnetic pulse. This pulse induces transient eddy currents in the pipeline wall, which then decay over time. The decay response is measured and analyzed to infer material thickness and metal loss. A key characteristic of PEC is its ability to penetrate non-conductive and non-magnetic layers such as coatings, insulation, concrete, seawater, and marine growth. This makes PEC particularly suitable for subsea pipelines where surface preparation is impractical. From a speaker standpoint, it is important to clarify that PEC does not produce a visual image of defects. Instead, it provides an averaged wall thickness measurement over the probe footprint. PEC is therefore best understood as a corrosion screening and condition monitoring tool rather than a precision defect sizing technique. The operating principle of PEC is based on electromagnetic induction and diffusion theory. When the probe transmits a rapid magnetic pulse, a primary magnetic field penetrates through coatings and seawater to magnetize the steel pipeline. When the pulse is switched off, the collapse of the magnetic field induces eddy currents in the steel surface. These eddy currents initially concentrate near the surface and then diffuse through the wall thickness toward the back wall. The rate at which the induced currents decay is directly related to the remaining wall thickness and material properties. Thicker sections cause slower decay, while areas with metal loss produce faster decay responses. The measured signal is analyzed using time gates to estimate average wall thickness. We should focus on liftoff affects spatial resolution but not penetration capability. As liftoff increases due to coating or concrete, the probe footprint increases, reducing sensitivity to localized defects. This explains why PEC excels at identifying general corrosion trends but struggles with small pits or sharp defect geometries. PEC offers several capabilities that align well with subsea pipeline inspection requirements. It can inspect through thick non-conductive layers, including coatings and concrete weight coating up to several hundred millimeters, depending on probe configuration. PEC can be deployed by divers or integrated into ROV-mounted crawlers, enabling inspection at significant water depths without the need for dry access or insulation removal. The technique provides repeatable measurements suitable for corrosion monitoring and trend analysis over time. PEC is also inherently safe, as it does not involve ionizing radiation, making it easier to deploy in congested subsea fields. From an operational standpoint, PEC allows relatively fast coverage compared to radiography, making it suitable for long pipeline sections. Despite its advantages, PEC has important limitations that must be clearly understood to avoid misuse. The technique provides an average wall thickness over the probe footprint, which can mask localized corrosion such as narrow pits or grooving. PEC is also sensitive to geometry changes, such as pipe supports, weld caps, and anodes, which can complicate signal interpretation. Thickness accuracy is typically lower than UT, often within plus or minus 10 to 20%, depending on calibration and liftoff. From an engineering perspective, this means PEC data should not be used directly for fitness for service calculations or acceptance decisions. We should focus on stress that PEC is a screening tool and must be complemented by higher resolution methods for defect characterization. Misapplication of PEC as a standalone acceptance tool is a common integrity management error. Subsea Digital Radiography Testing, SDRT, is a radiographic inspection technique that uses digital detectors instead of traditional film to produce real-time or near-real-time radiographic images. In subsea applications, SDRT systems are typically deployed using ROVs and utilize either X-ray generators or gamma sources. The radiation passes through the pipeline and is captured by a digital detector array, producing an image that reveals internal and external wall loss, weld defects, and other volumetric anomalies. Unlike PEC, SDRT provides a visual representation of defects, enabling precise sizing and characterization. We should highlight that SDRT is fundamentally an imaging technique, making it suitable for confirmatory inspection rather than broad area screening. The operating principle of SDRT is based on differential attenuation of ionizing radiation as it passes through materials of varying thickness and density. Areas with metal loss allow more radiation to reach the detector, appearing as darker regions on the radiographic image. Digital detectors convert radiation into electrical signals, enabling immediate image visualization and post-processing. In subsea environments, water introduces scattering and attenuation effects that can degrade image quality, requiring careful setup and exposure control. SDRT excels in its ability to detect and size localized defects, including pitting corrosion, wall thinning, and weld-related anomalies. It provides permanent digital records that can be archived and reanalyzed. SDRT is particularly valuable in critical locations where precise defect dimensions are required for fitness for service assessment. We should have full concern on that SDRT is not intended for long-length inspection due to time, cost, and logistical constraints, but it offers unmatched resolution when applied selectively. The primary limitations of SDRT in subsea environments are cost, complexity, and safety. Radiation safety management underwater is challenging and requires strict procedural controls. Deployment typically involves specialized ROV tooling, increasing vessel time and inspection cost. Inspection speed is slow, making SDRT unsuitable for large area screening. We should using SDRT as a primary inspection tool for long subsea pipelines is rarely justified from an engineering or economic perspective. PEC demonstrates a high probability of detection for general wall loss and broad corrosion features, typically in the range of 85 to 95% for metal loss exceeding approximately 20%. POD decreases significantly for small, localized defects due to spatial averaging. Speaker notes should clarify that POD values are influenced by probe selection, lift-off, and calibration quality, and that PEC POD is generally sufficient for screening purposes but not for acceptance decisions. SDRT offers high POD for both general and localized defects, often exceeding 90% when inspection geometry and exposure parameters are optimized. Its ability to visually resolve defect morphology gives it superior reliability for sizing and characterization. Speaker notes should emphasize that high POD comes at the cost of limited coverage and higher operational risk. This slide synthesizes the comparison between PEC and SDRT across key criteria: coverage, resolution, safety, cost, and POD. PEC provides fast, safe, and cost-effective screening through coatings and marine growth, while SDRT provides high-resolution defect characterization at selected locations. Speaker emphasis should reinforce that the methods are complementary rather than competing. Industry best practice for subsea pipeline inspection follows a two-stage strategy. Stage 1 uses PEC as a screening tool to identify areas of potential metal loss. Stage 2 applies SDRT or other high-resolution methods at selected locations for confirmation and sizing. Speaker notes should align this strategy with risk-based inspection frameworks and lifecycle integrity management principles. The engineering recommendation is to select PEC as the primary subsea pipeline inspection method due to its coverage capability, tolerance to coatings, safety, and cost efficiency. SDRT should be reserved as a secondary, targeted method for defect characterization where PEC indicates potential integrity threats. Speaker notes should emphasize that this approach is defensible during audits and consistent with offshore industry practice. This slide explains why SDRT should not replace PEC as a primary tool. While SDRT provides superior resolution, its limitations in speed, cost, and safety make it unsuitable for large-scale screening. Speaker notes should caution against over-reliance on high-resolution methods without considering inspection coverage and risk. This slide presents a direct comparison between PEC and SDRT techniques for subsea pipeline inspection. The table highlights key performance criteria that are critical in offshore inspection environments: coating or concrete penetration. Starting with coating and concrete penetration, PEC performs excellently because it can inspect through coatings without removal. In contrast, SDRT is more limited when coatings are thick or complex, which can restrict its applicability subsea. Marine growth tolerance. PEC is highly tolerant to marine growth, meaning minimal cleaning is required before inspection. SDRT, however, needs surface preparation and cleaning to ensure accurate results. Inspection speed. PEC offers fast screening capability, making it ideal for covering large areas efficiently. SDRT is slower due to the detailed scanning process and operational constraints. Resolution. One limitation of PEC is its relatively low resolution. It provides average metal thickness rather than detailed defect sizing. SDRT excels here, offering high-resolution imaging for precise inspection. Detection of small pitting. PEC has limited capability for detecting small pitting defects. SDRT performs better in detecting small and localized defects due to its higher resolution. Cost. From a cost perspective, PEC is generally more economical, especially for large-scale screening. SDRT tends to be very expensive due to equipment complexity and operational requirements. Safety. PEC has a key advantage in safety since it does not use radiation. SDRT involves radiation, which introduces safety risks and requires strict regulatory controls. ROV deployment. PEC is commonly deployed with ROV systems and is well established in subsea operations. SDRT can also be deployed but is more complex and less common in subsea environments. Probability of detection, POD, DOT, for general corrosion. Both methods perform well, with SDRT having slightly higher detection capability. However, for small defects, SDRT significantly outperforms PEC due to its higher resolution. Conclusion or key message. In summary, PEC is best suited for fast, cost-effective screening over large areas with minimal preparation. SDRT is more suitable for detailed inspection where high resolution and precise defect detection are required. The choice between the two depends on inspection objectives, budget, and operational constraints. This slide focuses on probability of detection, or POD, comparing PEC and SDRT under real operational conditions. The key point here is understanding not just capability, but realistic detection performance in the field. General corrosion POD. For general corrosion, both techniques perform strongly. PEC achieves approximately 85 to 95% detection probability, which is very good for area screening. SDRT is slightly higher, around 90 to 98%, due to its higher measurement A. Localized defects POD. The difference becomes more significant when we look at localized defects, such as pitting. PEC drops to roughly 50 to 70% because it averages thickness over a larger area. SDRT performs much better here, with 80 to 95% detection, thanks to its higher resolution. Key insight, main message. The key takeaway is the role each method plays. PEC is very effective at identifying where corrosion exists. It's a screening tool. SDRT, on the other hand, Practical interpretation. In practice, these methods are often complementary rather than competing. PEC can be used for fast scanning and prioritization. SDRT can then follow up on critical areas for detailed assessment and decision-making. So ultimately, it's not about choosing one over the other, it's about using the right tool at the right stage of the inspection strategy. Inspection method selection must balance technical capability with risk reduction and cost control. PEC minimizes inspection risk and cost while providing sufficient data for decision-making. SDRT increases confidence at critical points. Speaker notes should frame this balance as a core engineering responsibility. Key takeaways include understanding inspection objectives, recognizing the complementary nature of PEC and SDRT, and avoiding single-method inspection strategies. Speaker notes should reinforce that inspection effectiveness is measured by integrity outcomes, not technology sophistication alone. In conclusion, PEC should be selected as the primary subsea pipeline inspection method for corrosion screening, with SDRT applied selectively for confirmation and sizing. This integrated approach delivers optimal safety, reliability, and cost-effectiveness and aligns with modern offshore integrity management practices. Speaker notes should close by inviting technical discussion and site-specific adaptation of the strategy.